In section 1.9, we're going to continue talking about linear transformations, and this time focusing on the matrix associated with the linear transformation. In section 1.8, we focused on, given a linear transformation as matrix multiplication, what happens? We will now show that we can write any linear transformation as matrix multiplication. We're going to look at how to find that matrix. So note that in this section, we're only going to cover until theorem 10 in the book, the first part of this section. And we're going to introduce something important in linear algebra, which is the identity matrix, which we are going to denote I sub n, and that is the n by n matrix with ones on the main diagonal and zeros elsewhere. The ith column of In is labeled E sub I. That is a vector E sub I. Now you might see a resemblance. The identity matrix is something that we've seen before. This looks like what we want to get in row reduced echelon form to solve a system of equations. We will look at that in a future section and the importance of that. But right now, let's look at this example. We have I sub 3 is the 3 by 3 identity matrix having three vectors E1, E2, E3 with ones on the main diagonal, zeros above and below that main diagonal. And the importance of the identity matrix is seen in this next example. If I have I times any vector x, any three-dimensional vector x, then I can write this as a linear combination of the entries of that vector. So this will be x1 times 1, 0, 0, plus x2 times 0, 1, 0, plus x3 times 0, 0, 1. Noting that these three column vectors are E1, E2, and E3. And if we bring them all together, if we multiply across, we get x1 times 1 plus x2 times 0 plus x3 times 0 will just be x1. And similarly for x2 and x3, in fact, we just get the vector x back. And that's what's so important about the identity matrix is that, in general, for any x in Rn, if we take the n by n identity matrix times x, we always get x back. We can think of the identity matrix as the number 1 in the real numbers. If you take 1 times any number, you just get that number back. In fact, if we think about the first identity matrix, it really is just the number 1. And if you take an identity matrix times any vector of the appropriate length, we get that vector back. Another definition are these E sub i's. We're going to look at those and call them the ith axis vector or the ith standard basis vector. We'll introduce standard basis later in this course. And E sub I is a vector in Rn with zeros in every entry except 1 in the ith entry. So E sub I is a bunch of zeros with a 1, and the 1 is in the ith entry. So I guess this would be E sub 4, corresponding to n equals 6. We call them the standard basis vectors. Let's look at an example in R3. Because they represent going 1 unit in the different directions. Let's say this is x, y, and z. These vectors represent just going on the axis 1 unit. This would be E1. This would be E2, 1 unit in that direction. And this will be E3. Now we can draw them nicely in 3 dimensions and 2 dimensions, but we can do the same thing in any dimension. It's just hard to draw a picture of it. And then one more result before we can really dive into material here. From section 1.8, the last section looking at linear transformations, we showed that if we have t of cu plus dv, we can write that as c times du plus d times dv. And we hinted that it really had to do with a linear combination of things. And we hinted that we have this next result, that we can do this for more than just two vectors and two scalars. We could have any linear combination of scalars and vectors, t of c1v1 plus c2v2 all the way to cpvp, would give c1 t of v1 plus c2 t of v2 all the way to cp t of vp. We can break up that linear combination and put the linear transformation as we want across it. With that in hand, we can now look at some examples here. So first example, the columns of I2, that is the identity matrix with n equal 2, are the two standard basis vectors, the two axis vectors, corresponding to the x and y direction, 1, 0, and 0, 1. And we're going to suppose that t is a linear transformation from R2 to R3, noting that R2 is the domain, that's what we plug in, two-dimensional vectors. We're going to output three-dimensional vectors, that being the codomain. And we're given this transformation by these two vectors. If I plug in E1 and E2, we have t of E1 is 2, negative 3, 4, and t of E2 is 5, 0, 1. And just with that information, we are going to compute t of x for any vector x in R2. So the way this is going to work is we can show that x can be built from these axis vectors, from the standard basis vectors. These are building blocks for any vectors, and we saw that in the last lecture a little bit. So given any vector x1, x2, we can write that vector as a linear combination of E1 and E2 by x1 times 1, 0 plus x2 times 0, 1. Or written elsewhere, written another way, x1, E1 plus x2, E2. So now we can see that if I have t of x, I can rewrite x as x1, E1 plus x2, E2. And then using our linear combination result, I can write this as x1 times t of E1 plus x2 times t of E2. And I know what those two vectors are. We're given them in the problem. So this is some vector equation. We can write it as matrix multiplication by just putting this as 2, 5, negative 3, 0, 4, 1 times the vector x1, x2. Or we can think about this as a vector A, or a matrix A, times x. So on the next page, we see this matrix and this vector. So we can see again that if we want t of x for any vector, all we have to look at is t of the axis vectors, or these basis vectors, which are building blocks for our vectors. And that gives us this matrix that I can think of this linear transformation as matrix multiplication. So again, to get the matrix A associated with the transformation T, replace the identity matrix E1, E2 with T of E1, T of E2. And in general, this would be for any n-dimensional vector or matrix. So here's our theorem in generality. Let T be a linear transformation from Rn to Rm. We input n-dimensional vectors, we output m-dimensional vectors. Then there exists a unique matrix A such that T of x equals A of x for all x in Rn. In fact, A is going to be the m by n matrix whose jth column is the vector T of Ej, and Ej is the jth column of the identity matrix. So we can see that A is based on these column vectors, which are built from taking T of the axis vectors or standard basis vectors. And this is called the standard matrix for the linear transformation T. Thinking about back to section 1.8, in that section we often thought about our linear transformation as matrix multiplication. Here's our matrix. This is a linear transformation. Now we're saying that given any linear transformation doesn't have anything to do with matrix multiplication possibly, we can think of it as matrix multiplication, which we can have a lot of tools at our disposal for. And we're going to see some examples of things that are transformations that have absolutely nothing to do with matrices that we're going to put into this matrix idea. So another example, let's say that I have this linear transformation, should be an equal sign here, x1 minus 2x2, 4x1, 3x1 plus 2x2. This is what happens when you plug in a two-dimensional vector. You get a three-dimensional vector out. So note this is a linear transformation from R2 into R3. We're inputting two-dimensional vectors. We're outputting three-dimensional vectors. And we're going to try to find what is the matrix A associated with that linear transformation. What is the standard matrix of the linear transformation T? Well, to find that, all we need to do is look at T of the standard basis vectors, T of the axis vectors, T of the columns of the identity matrix. All of those are the same thing. In this case, since we have a two-dimensional vector, T of E1, T of E2. So again, that is saying that we are going to look at T where I plug in 1, 0, and T where I plug in 0, 1 in for x1 and x2. So that matrix will be x1 is 1, x2 is 0. That's going to be 1 minus 2 times 0, 4 times 1, 3 times 1 plus 2 times 0. And then for the other one, I have T of 0, 1. x1 is 0, x2 is 1. That'll be 0 minus 2 times 1, 4 times 0, 3 times 0 plus 2 times 1. Those are the two columns for my matrix. Simplifying, that gives 1, 4, 3, negative 2, 0, 2. That is our matrix A associated with that transformation T. Again, built just from the vectors 1, 0 and 0, 1. So one last example here. We're going to look at something that has nothing to do with matrix multiplication and think about it as matrix multiplication. So here we're going to find the standard matrix of the linear transformation T, which is just about rotating a point about the origin an angle of pi over 4 radians, remembering that pi over 4 radians is 45 degrees, counterclockwise around the origin. So this has nothing to do with matrix multiplication, and yet we're going to think about a matrix in this. And to do that, again, we're going to look at our standard basis, our axis vectors, our columns of the identity matrix, 1, 0, and 0, 1. So let's see what happens when I think about the vector 1, 0, that being E1, and the vector 0, 1, E2. What happens when I rotate those pi over 4 radians, or 45 degrees, counterclockwise? Well, we get a new vector out, a new point associated with that vector in both cases. And that new point is going to be a point on the unit circle. We could draw that unit circle here. So that is a unit circle, and if I rotate that vector of length 1 around the origin, I'm just going to land somewhere else in that unit circle. And the point that that's associated with is, from trigonometry, we know that this is going to be cosine of the angle pi over 4 sine of pi over 4. That is the x-coordinate and the y-coordinate on that unit circle. We could build some triangle to find those values, building it down from there, thinking about that. But that's going to be, in this case, 1 over root 2, 1 over root 2. Or you can think about that as square root of 2 over 2. That's the same thing. So that means that if I take the transformation and I plug in E1, I'm getting out 1 over root 2, 1 over root 2. Now let's do the same thing for the vector 0, 1. Note that when I'm rotating pi over 4, this is actually corresponding to the angle 3 pi over 4, or this is pi over 4 plus 90 degrees pi over 2. And the angle associated with that, or the point associated with that, write it down here, is going to be cosine of that angle, 3 pi over 4, sine of 3 pi over 4. And in that case, that is negative 1 over root 2, 1 over root 2. And that is the entries of T of E2 there. So our matrix A is those two column vectors put together, 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2. And note that this is equal to cosine of pi over 4, sine of pi over 4, cosine of 3 pi over 4, sine of 3 pi over 4. And there's our matrix A that's associated with this rotation transformation, which means that if I want to figure out where any vector goes with some transformation, I will multiply it by that matrix, and I will see where it goes. It doesn't have to be anything with length 1. It can be any vector in two-dimensional space. Let's look at this rotation again. On the next page, we'll see that this is actually called the Gibbons rotation by an angle theta going counterclockwise. And we showed that the matrix will be cosine of theta, sine of theta, and then cosine of theta plus pi over 2. That's that 3 pi over 4. We have to go the 90 degrees first. And sine of theta plus pi over 2. And this is often written as this matrix right here. Cosine of theta, sine of theta, negative sine of theta, cosine of theta. And I wanted to take a second and just remind you where that negative sine and cosine come from in the second column. So note that if I look at the function cosine of theta in this first graph here, and I look at instead cosine of theta plus pi over 2, that is a horizontal translation of cosine of theta, pi over 2 units in the to the left in the negative x direction. And if I sketch that function out, the dotted yellow line here, that gives me cosine of theta plus pi over 2. We might be able to see that that's just the same thing as negative sine. It's sine flipped over the x-axis. That's where that first identity comes from. Cosine of theta plus pi over 2 is equal to negative sine. And furthermore, if I have sine of theta and I move it to the left pi over 2 units, that gives me exactly cosine out. These are called cofunction identities. You may have gone over them in a pre-calc course. The reason why we have sine and cosine, the names are sine and cosine, is because they are translations of each other. Secant and cosecant are translations of each other, and tangent and cotangent are translations of each other. That's where those names come from. We're using them here to get this matrix. This is a useful matrix to know. You're not going to be expected to know the trigonometry behind it. That's just to show where it comes from. But we will be using this matrix in the future.